Yeah, so this is about a very basic system, just a single qubit. The work was done in a big program funded by IARPA and then DARPA. So yeah, some of the people here, including Paul, were part of this program, and it was a large collaboration. So the main wow, is that? Okay, so yeah, so everybody here was involved with the various aspects of this experiment, but I wanted to mention in particular the work done by two of the members of my group. Shidai, a senior graduate student who is close to finishing his PhD. So he did pretty much all of the modeling and analysis of the data, also running some experiments remotely. So the location of the experiments was the Lincoln Lab, MIT Lincoln Lab in the US. And then Robin Trappen, who was a postdoc for about a year and a half in our group. So yeah, so they were the ones who really led this effort on the experiments. This is the outline of my talk. I will start with an introduction to the Landau-Zener problem. Then I will talk about the experimental setup that we are using. This is a capacitively shunted flux qubit. I will talk about a couple of the technical details around this, so how you do flux calibrations and how you characterize coherence. And then the main topic is going to be the discussion of the experiments on the Landau-Zener transition probability versus the strength of tunneling in the two-level system. I'll then talk about the theoretical modeling of these experiments, and then I will close. And this is actually quite fresh. So I had some results sent on this as basically yesterday, the final, not final, but final enough for this talk, let's say. Yeah, we are quite excited about this part because we feel that here we are actually finding a way to understand the physics of what is a relatively complex open system setting with some relatively basic intuition. So let's get to it. So Landau-Zener. So this is a crowd that does know everything about it. So the Landau-Zener problem has been known for a long time. So for a two-state system, if you go through this anti-crossing, basically the Hamiltonian is written here. Delta is the tunneling between two states. You can call them left and right. And this term here describes how you go through this anti-crossing with the minimum energy level splitting delta. So in the coherent limit, the probability for the system to remain in the ground state is given by this expression. So it's the exponential minus pi, the gap square, divided by the sweep rate v. So now Landau-Zener dynamics is important because it applies to lots of physical systems, including chemistry. So it's applied to phenomena in chemistry, molecular magnets, and of course we are interested in it because of quantum annealing. And of course it's been known for a long time that the Landau-Zener dynamics is affected by dissipation, and there was a lot of work done over the years on modeling dissipation. I think my slides are still moving. Okay. All right, so I'll just try to manage it. Maybe that was accidental. Okay, so yeah, so we are interested in aspects of how you model the basically the Landau-Zener transition in an open system setting, and basically the key point of this talk is that we looked at the difference between what we call the weak coupling and strong coupling regimes to the environment, and I'm trying to give here a basic picture for what weak coupling means. So when you go through this transition, you basically sweep your longitudinal field, and pretty much at any point during this traversal of the anti-crossing, your system has coherent evolution. So that's described simply by the Hamiltonian that I showed earlier. But in addition to this, you have transitions between the energy eigenstates of the system. So you have a downward rate in blue and an upward rate in red. What is important here is that there is no environment memory. So the environment keeps changing its state, and that state does not depend, in a sense, much on the state of the qubit. You have these transitions rates that are dependent on the environmental spectral function, so that's essentially related to the Mohs density and the coupling to the system. It depends on the coupling operator matrix element, so that's the coupling operator belonging to the qubit or the two-level system, and these rates are described by detailed balance. And of course, a very important thing here is that if the coupling is longitudinal, then these rates are suppressed by this factor, the tunneling amplitude delta divided by the transition frequency all squared. So this really means that as you go very far away from the symmetry point, your rates tend to become very small, and thermalization starts to become very ineffective once you go past this crossing. So more formally, you model this with this coupled system environment Hamiltonian. So sigma z is the system operator, q is an operator of the environment. Then you have the transition rates are given by a Fermi-Golden rule kind of expression, or what you get in the Markov approximation. And if you model such a system, you can use various tools. Here we focused on the use of the adiabatic master equation, and some results from this reference one over here are shown in this graph. So just to start with the case, say, of very small environment temperature, you see, so basically what is plotted here is the probability, the Landau-Zener probability to go to the, to stay in the ground state as a function of the sweep velocity. So when the sweep velocity is very large, this probability is 0, but as the sweep velocity goes down, the probability becomes 1. So this curve here is essentially the coherent Landau-Zener limit, the red curve. Then as the temperature increases, things are changing, and in particular what is to note here is the fact that at some point you have this non-monotonic behavior of the transition probability as a function of the sweep rate. So you can think of the sweep velocity as being, of course, it is proportional simply to the inverse time. So these are short evolution times, these are long evolution time at this end over here. So what is happening when you have a finite temperature, and if the coupling is large enough, this is the environmental coupling factor here. Basically, in this limit here of short evolution times, you are very close to the coherent limit. This makes sense because the system doesn't have much time to interact with the environment. Then if you go a bit further, what you observe is that there is essentially an increase in the probability of the excited state. And this has to do primarily with thermalization near the gap. So at the gap, that's where the coupling factor favors the transitions induced by the environment, and that's when the effect of the environment is strongest. But then as you go further, the probability to stay in the ground state starts to come back very, very slowly, but it starts to come back to 1. And this is simply a result of the fact that the longer you make the sweep, the bigger the chance for the qubit to go back to its ground state. If you simply do this slowly enough, eventually it will go to the ground state. But this can be a very very slow transition. So this is what happens in the weak coupling limit. So now the strong coupling limit is something that is less common when I talk about open system dynamics. So I try to do my best here to kind of show a cartoon picture of how you might think about a strong coupling scenario. So here you start with, say you start with a system in the ground state, and say that there was either as a result of the coherent Landau-Zener either coherently or incoherently, it ended up in the excited state. So here, basically, I think I focused so much on aligning these graphs here that I messed something up. Okay, what I messed up was that this was meant to be reversed. So imagine flipping this along its vertical axis here. Sorry about that. So flip this, and you would end up with the left state. You would end up with this, with this curve over here. Okay. So basically, the system is in the left well. Left well is supposed to be higher, so it goes like this. Okay. So it's as this one over here. So sorry about that. I messed this up. Okay. So basically, you are in the left well. The left well is higher up in energy as opposed to this one diagram here, which is wrong. The rest are correct. Okay. So it's in the left well. The left well is higher in energy. And basically, because the qubit is, in order to go from left to right, actually I'll focus on this one, say it was here, in order to go from left to right, so in the limit where the coupling between the qubit and the environment is very strong, and rather the tunneling amplitude is very weak, these transitions have to conserve the energy of the qubit and the environment. So basically, when the qubit goes from here to here, and if the environment is in the ground state, so basically the environment follows the qubit and it settles to a state which is sort of close to its ground state, then when the qubit goes down in energy, the environment has to come up in energy in order to conserve energy during that process. So now this state is different from the initial state, both in being, so from the point of view of the environment, the qubit acts kind of like a parameter. So you can imagine that it shifts the origin of a harmonic oscillator, which is what I'm trying to represent here. But also the energy for this different harmonic oscillator ends up being above its ground state. And once that happened, now if the environment has a dynamics that is fairly quick, so quicker than it would take the, is this still?
You're having some interesting technical
Yeah, indeed, very,
Change your battery. Sorry.
very appropriate for the last stop on Friday. So,
Carry on. I'll get this fixed.
okay, so all right. So basically, once the environment made it to this different excited state, it can have enough time to actually relax. And once that happened, there is not enough energy for the environment to kick the qubit back in the other state. And in a way that makes it, so what's different from the usual weak coupling scenario is that it takes a bit more than just the thermal fluctuations. It also takes for the environment to be kind of in a particular state and has enough energy in order for this reverse process to happen. And this is what distinguishes, so once you made it to, thank you. So once you made it to this state here, this is what distinguishes this from the kind of usual weak coupling scenario. Yeah. In Canada, we usually have a hockey stick at hand to point to things on a screen. So, okay, so I think I'll just, can you see my, oh, actually I can show this as a laser. Okay. Oh, okay.
Sorry about this, Adrian.
Oh, no worries. Okay, here it is. So, okay, so let me do this. Okay, so, yeah, so basically, once the environment made it to this ground state, there is, oh, thank you. Okay, so thanks. Okay, so yeah. So once the environment is here, it's basically very hard for the qubit to come back because you would have to, in a way, rebuild this energy of the environment and a particular configuration that allows the qubit to come back. So I'm hoping this gives kind of a reasonable intuitive picture for what is meant here by the strong, what we call the strong coupling limit. So the key point is this dressing by the environment and the fact that the qubit has such a large effect that when transitions happen, they can be followed by this irreversible dynamics of the environment. So now, the strong coupling limit was investigated in various contexts in chemistry and other areas, and there was in particular a lot of work done by the D-Wave group on this. A lot of very insightful physics experiments were done with both single qubits and multi-qubit systems. And basically, the kind of experiments that are done are about measuring the transition rate from the left to the right well as a function of the bias between these wells. They got their order of wells right here. So if you go from the excited from the higher energy to the lower energy, you basically need a bit of extra bias for this transition to happen. And if you go, say, if you put the left well up, you'll have a transition that has a maximum rate at a shift that is called the reorganization energy of the environment. So there is this peak over here. And if you go with a sweep the other way around, so you start with the right well up, you have a maximum that is shifted in the opposite direction. And both this shift and the width of this curve are related to properties of the noise in the system, which have been very carefully quantified in these experiments done by the group at D-Wave. So now, so these are more detailed measurements of the rate over a range of fluxes. One particular condition for the strong coupling limit that is used here and applies to these experiments is that this width, so that essentially this is the magnitude of the environmental noise, is larger than the tunneling gap delta. So in a way, this means that the qubit is defaced so quickly that you can't really build superpositions of flux states. And this is what makes this picture where you think about transitions between flux states, so left and right states, accompanied by dressing by the environment to be kind of the proper energy, the proper basis for this incoherent dynamics. So once you have this model, you can determine the transition, the probability to stay in the left state using a simple rate equation. Again, these are calculated rates as an example over here. And one thing that is quite intriguing is that in a particular case, so here let me start by saying maybe, so this is the Landau-Zener probability again. So the coherent case here in blue, so that's the probability to stay in the 1 minus the probability, to stay in the left state as a function of the sweep time. So we go from 0 to 1, as I showed before. Now, what is very interesting is that when you are in the very strong coupling limit, and if you also have this condition, namely the environment reorganization energy is larger than the noise amplitude, basically your transition probability as a function of time becomes essentially has the same form as the Landau-Zener form, essentially as the fully coherent form, although the physics is completely different. So you basically recover the same type of probability as you have in the fully coherent case. And this, so there's been work on this topic done more using more general treatments, using, for example, the polar and transform master equations, and there was also a very interesting work done with multiple qubit systems a while back, again at D-Wave. Okay, so when did I start at 3? I have
a couple of minutes after 3, maybe.
Okay, yeah. I feel like I probably need to speed it up a bit. So we're interested in all of this because of quantum annealing. And there was a lot of work, of course, done in quantum annealing where the role of coherence was identified as being very important. We've seen the very interesting talk by Andrew yesterday on phase transitions, where essentially the evolution is described very well by the Schrödinger equation. There are also studies that where the experiments were well described with models based on the weak coupling or the strong coupling limit. So in the experiments we did, we explored something that is kind of in between the two cases, which we believe has never seen before, and we think it helps us get a bit more insight into the physics of this system. Okay, so to talk briefly about the qubit, it is a flux qubit. You've seen quite a bit on this. So it's a capacitively shunted flux qubit with two control loops. One of the loops controls the tunneling strength, and the other loop controls the bias. This is a circuit wrapped around it in order to control it and read its state. And this is a picture of the chip design. So here basically we can look at Landau-Zener physics. We can change this bias in between the two wells, and we can also change this tunneling amplitude delta with the knobs we have in the system. Okay, so this is the part that I'm definitely going to have to skip. I think mostly, I just want to say that there are a few very important ingredients here, so that's probably more interesting for experimentalists. But basically, yeah, flux crosstalk calibration is a big issue, so you need to know which magnetic fluxes you are applying in the different loops. But flux is very difficult to contain in general, and we had to do a lot of work to do this. The idea is simply that you're applying some controls, and then then the actual fluxes in the loops are just linear combinations of that. So it's as simple as this. But to actually find out what this linear transfer function is, it's quite complicated, and we've been through quite a long series of experiments where we explored two approaches to do this. One is based on essentially kind of closing in on the real coupling matrix by iterating on what you're finding in each run. And then another was basically to rely on a very fundamental property of the flux, namely that the response of the circuit is periodic in flux. And if you just use that property, you can actually use optimization on the real experimental system to find your coupling matrix. And I think I will not say a lot more about this. Except that, yeah, this worked for a very large system as well, so we're quite confident that, yeah, it's a good approach. This shows a result on 27 loops and 27 coupling bias lines where this worked pretty well. So I think I will leave it here just to have enough time to go through the more kind of central parts of the talk. Another point I want to explain a bit is that in order to control the system, we had to do very detailed analysis of, how does the circuit work. So we did very detailed spectroscopy experiments. So that's one thing that is, for example, specific to these experiments, namely that we could also use high-frequency signals to understand the spectroscopic structure of the system. So this shows the frequency as a function of the control flux phi x, which tunes the tunneling, and phi z, which tunes the bias. And we found a great fit as a function of those two parameters for our circuit model. And then the other key point was to do decoherence measurements. So typically, decoherence measurements are done in the weak coupling limit. So that's where if you measure a rate between two states, that rate can be connected to circuit parameters and then the power spectral density of your noise. So those experiments allow you to extract the power spectral density of your noise over a very broad frequency range. And what we find is nothing surprising. It's just validating things and extracting a few numbers. We have 1/f noise at low frequency, and then we have additional high frequency noise. And these are figures for 1/f noise, which again are fairly standard for these devices, and essentially we're going to be relying on these numbers to explain the experiments. So now let's look at the Landau-Zener experiment. So here this graph shows the probability of the excited state as a function of the Landau-Zener, as a function of the time to go across the anti-crossing. So you see that for each of these curves, the probability decreases. So that's the probability to be in the excited state that is shown here. I think there's a couple of switches back and forth between ground and excited. This is the excited state probability. This becomes smaller as the time gets longer. Yes, okay. So this becomes smaller as the time gets longer. And in this short time limit over here, we can fit all of these curves with the Landau-Zener formula. So basically, the sweep rate depends on the TLZ time, and we see. So again, this is a logarithmic plot versus the time shown linearly. So this allows us to. This is in perfect agreement with this formula. And moreover, one other thing we can do, since we know the IP parameter and the flux coordinates at the beginning and the end, which define the sweep rate, we can extract the gap of the system. And here what was interesting is that we can also measure this gap, the gap delta, spectroscopically, and we did this. So this is shown here for frequencies at 1 gigahertz and higher, where we could measure spectroscopy on the system. So using that data, we could do a fit of the circuit model. And then when we look at our gaps from the Landau-Zener tunneling experiments, we see that that's in perfect agreement with the circuit model, so we cannot measure here spectroscopically, but this follows the best fit pretty well. So, but now let's look at what happens over longer range of time scales. So again, the axis is different here in that we show the ground state probability. This is shown as a function of the time to go from left to right. Which is shown logarithmically. So now each of these curves here, so each color corresponds to a different setting of the flux phi x, which in turn corresponds to a different value of the delta parameter. So that's the tunneling between the two flux states. So if you go in this direction here, the parameter delta increases. So as you can see here, so if you start at the large values of delta, the ground state probability is small at first for short sweeps, but then it becomes large, and it nearly follows the coherent limit, which is given by the continuous line over here. But as the time becomes longer and longer, we see how the ground state probability does not continue to increase. In fact, it even starts to decrease. My goodness. It starts to decrease, and then it starts to come back up again. And this is in line with what I was showing earlier about how at long time scales you start to see how the two-level system re-equilibrates again. So there is a come down in this ground state probability simply because you give enough time to the system to relax. So this is what we see as a generic behavior for these relatively large values of the gap. So these are these colors here, so starting from orange and into light green. But as you make the gap smaller and smaller, so that's going towards blue here, we see a similar trend. So again, this follows the Landau-Zener formula, but then there is no decrease in probability. So actually the probability to stay in the ground state follows monotonically the time. So you don't have this decrease anymore, which is a trademark of this weak coupling limit with the rationale I discussed earlier. Namely, you have some intermediate time scales where you get thermalization, long time scales where you gain again in the ground state probability simply because you give the system time to relax. So we set out to explain these experiments quantitatively. So for this, we are using this model of coupling to the environment. So coupling is longitudinal, namely to the flux basis or the qubit position basis. And we use a combination of 1 over F noise and ohmic noise and this bath temperature. All of these parameters are extracted from experiments and again are generic for flux qubits. So the first type of simulation, so what is here on this slide is just simulation. So it looks exactly like the data, except it doesn't have noise. It has the same colors, though. So the colors correspond to what you showed earlier. So red or orange is large gaps, and blue is small gaps. And these are numerical simulations that show, again, the excited state probability as a function of time. And we clearly see how for most of these curves, you have this behavior where basically there is an increase and then a decrease and then an increase again in the ground state probability as we make the times very long. So this is the weak coupling limit. Now, if we do the same numerical simulations with the strong coupling model, and in particular this uses the polar and transform master equation, so this takes into account the high frequency noise and how it renormalizes the qubit frequency. We see something similar, but with a very important difference. Namely, in none of these simulations here do we see this non-monotonic behavior that is characteristic of the weak coupling limit. Rather, the ground state probability keeps going up as the time goes up. And if we put everything together now on the same slide, so let me make sure that, so again, so it's important that the free panels are firstly data, then the AME, so that's a adiabatic master equation with coupling limit, and then PTRE, so that's the strong coupling limit simulations. So, and the black curves in each case are the coherent limits. So that's the Landau-Zener coherent formula, which takes you all the way to 1 if the time is long enough. Also, this is shown in terms of a renormalized time, which is essentially the proper time if you want to bring all the curves kind of on the same footing when you consider just the Landau-Zener formula. So essentially, this is the exponent, the dimensionless exponent in the Landau-Zener formula. Okay, so this is the normalized time, and what you see is the following. So if you look at all the cases, data or simulations, you see how at short times all these curves collapse because this is this dimensionless time. But then there are clearly some important differences between data and the weak coupling limit and strong coupling limit simulations. And in particular, we see how the weak coupling limit simulations, they have this feature that there is non-monotonic behavior. And moreover, all the points collapse at long time scales. And essentially, that's a kind of like a scaling property that has to do with how the noise couples to the system in this regime away from the symmetry point, where we have that suppression factor I mentioned earlier, namely delta over frequency square. So roughly that explains why we have this collapse of all the curves in this limit over here. Similarly, for the strong coupling limit, you have a collapse as well in this limit, which again is kind of like scaling behavior related to the properties of these equations, but you have no non-monotonic behavior. And clearly our data is right in between, in a sense. You sort of go from this case here to this case of strong coupling, but you have this overall trend that the curves gradually, so as you make the gap smaller and smaller, so here the gap delta is high, here is small, the curves gradually tend to go towards the coherent limit. And as I said earlier, this is kind of counterintuitive, but we know that for very strong coupling, the transition probability looks as in the coherent case. And that's what D-Wave measure typically in their devices, being in that strong coupling limit.
I have a question.
Yeah.
It's probably on the markers, but I cannot see them properly. Why do you have two branches on the strong coupling limit?
Oh, yes, sorry, I should have gone over that. Yeah, so the two branches are basically two strengths of the noise. So there are some challenges with being very confident with that noise amplitude, because you're measuring your noise amplitude over a frequency range, but you don't have really full visibility over the full noise spectrum. So this simulation here is done with what we extract directly from the experiment, and this is with the larger noise amplitude, which seems to explain qualitatively or semi-qualitatively things a bit better. Sorry, semi-quantitatively things a bit better. And yeah, but again, it's because that parameter cannot be determined very reliably. Yeah.
So can you use the data to actually get the measure of the noise, like the curves at the smaller gap?
Yeah. So that's what we are working towards. So basically in the final part of the talk, that's basically what I'm going to go. So we don't have a full answer yet, but we're starting to have something that gives us some more understanding on this. So this again summarizing the result. This is the same panels as before, but shown as a function of the time, not the normalized time. So again, the trends are large gap. We see this non-monotonic behavior in long time limit. In the small gaps, we see this monotonic behavior and essentially going towards the coherent limit. So now, in the final part of my talk, I wanted to tell you a bit about some work we did. So I showed you this picture of the strong coupling limit. And again, the physics of this, I've been thinking about it for more than a year. It's very hard. I mean, it would be nice to maybe have a model that allows you to understand, say an environment, and kind of understand what are the parameters of the environment that realize either of those two limits. And we've been doing this work where we thought of basically modeling our environment with a spin bath. So this is at least sensible based on the fact that flux noise is attributed to spins at the surface of the superconductor, and also 1/f noise that meets the model in terms of a bunch of two-level systems. And we wanted to use, for starters, we want to use a minimal spin bath model. So basically, we want to have a model that involves a spin such that this spin acts as a dephasing source for the qubit, and in particular, we want that dephasing to be fairly strong in order for this picture of basically the qubit being permanently dephased, let's say. And then you want to have at least two states of your environment that are meaningful, because you want to have some way to gauge this reequilibration dynamics of the environment. So we basically say we have two states that model that, and then we want to have a mechanism for that. And the model we are using is basically so it's the qubit coupled to its own bath, but then this qubit is also coupled to a spin, so that's capital S here, and this spin is in turn coupled to another bath. The coupling between the qubit and that environmental spin is easy coupling in this ferromagnetic, so negative J. The spin is taken to have no Hamiltonian of its own, so it only interacts with the qubit, and the interaction between the spin and its environment is via the X operator, and the environment of the spin is taken to have anomic bath. So there are two parameters that are important here. One is this coupling between the qubit and the spin. The other is the strength of the coupling of this environmental spin to its own bath, which is quantified by this parameter eta over here. So now just to look briefly, so if you forget about the environments of both the qubit and the spin, you have basically a two-qubit system, and this is the spectrum of it. So these are two qubits. I mean, the qubit and the spin, so two-level systems ferromagnetically coupled. So if you change the longitudinal field of the qubit, the energy spectrum looks like this. So you have a crossing here between left, and right, and then you have this anti-crossing over here. So here the states the first state is the state of the qubit, so that's left or right. The second state is the state of the spin, and we also call that left or right, although thinking of it maybe up and down would be better. But basically, the spectrum is quite simple, and we set out to do some modeling around the simple model. And what we see is actually quite interesting. So we start a kind of the trivial case where basically what you do is you set the coupling between the spin and its environment to be very small. So it's as if the spin did not have any environment. And then what happens is basically trivial because the spin has no dynamics of its own. So all it does is it acts as an additional longitudinal field to the qubit. So it basically just shifts the crossing position for the qubit. And basically that's what we see. So if we start with the qubit in its left state, so that's the green curve here, we see how at the effective crossing, which depends on the coupling to the spin, you have a sharp transition between the qubit being in the left state and then the qubit going to the right state with the spin state remaining left all along. So essentially it's just the Landau-Zener probability. And here we are including some environmental effects. And if we look again at the ground state probability, it goes up and it goes down. So this is essentially just the weak coupling limit with essentially looking at just the coupling of the qubit to its own environment. So just a weakly coupled environment of the qubit alone. Now, if you start increasing the coupling between the spin and its bath, you start to see something interesting. So here what is shown is the ground state probability as function of the total time to change the qubit bias, so going through the anti-crossing. This curve here in the middle is actual data from the experiment. So actually I'm not claiming, we're explaining our data. This is more like a guide to the eye, just to show the general trend in the data. So this is the data, and again, the continuous line is just the Landau-Zener. So if you set the coupling between the spin and the environment to be fairly weak, you see this ground state probability coming up, and then it keeps increasing, but at a slower rate. And then as you make this coupling between the spin and the environment stronger, you have a similar trend, but then this comes a bit closer to the data. And then we keep increasing this coupling, and it keeps coming closer to the data up to some point where it goes even farther and it approaches this coherent Landau-Zener limit. So now if we look at the dynamics of the qubit plus spin system throughout this time, we see essentially the kind of effect that we think is a trademark of this strong coupling limit. And to go, I think I am, okay, so I'm at about 35 plus, I think, right? Is that reasonable still? I think I'm a few minutes away from finishing. Okay, thank you. So, okay, so just to get me to explain this properly here. So you start with the qubit in its left state, right? So that's the ground state of the qubit at the left of the anti-crossing. And with the coupling being ferromagnetic, the spin settles in the left state as well. So the probability of the left is 1, and all the other states are unoccupied. So now you're approaching the crossing point, and what happens there is that the left state makes a transition to the right-left state. So essentially here, the qubit goes from the left to the right well. So that's basically the qubit changing its state, but the spin remains in its left state. So the spin does not change state. But then if you keep going, at this point the spin basically it sees a bias from the qubit. So the fact that the qubit changed state means that the spin has effectively a new energy. And that energy is to be given away to the environment. So if you follow this probability here of the state right-left, you see how this probability drops. And while it drops, we see that the probability of the state right starts to come up. So basically you lose the probability of right left, and then you gain probability in the state right. So basically the spin gave away its energy to the environment. So this, in a way, emulates this reequilibration of the environment that I was discussing earlier in context while looking at that initial picture for the strong coupling limit. And once that happened, then nothing else happens. Basically, the qubit is locked into its right state. I mean, with some probability, but there's no dynamics anymore. And, well, actually, this is a zoom in that would have been a bit better if I used. Okay, again, as I said, I didn't make most of these slides. And, okay, so now, yeah, then just to also now look at, so say you have this model and the coupling of the spin to its environment is fixed and fairly strong. It's interesting to look at the role of the qubit gap, so the tunneling between the two qubit states, the parameter delta. And this graph here shows essentially how the probability versus time goes as a function of the gap, qubit gap delta. And here again is the same direction of color, so go from large gap, so orange, to small gap, light blue. And we see, so if we take at the same time two different tunneling gaps, we see clearly the distinction between the sweep coupling limit and this strong coupling limit, where you give the energy to the spin and that energy is taken away. So that's the same coupling to the environment, but then just the qubit gap being different makes a difference, because essentially the way the spin interacts with the environment remains the same, so it has the same time to give its energy away. But the fact that the qubit is, in this second case here, slower means that there is time. Means that the qubit does not evolve, and the spin has time to yield its energy to the environment. Yeah, and this shows, so again, this is not a claim that we are explaining the data, but rather just show that it's plausible that a model with, say, maybe not one spin, but several spins is enough to explain, at least qualitatively, what happens in experiments. So again, this is our experiment, and this is this model with some carefully chosen parameters. And this is basically what I want to present. So yeah, so we're interested in this because it's for us, it's kind of so as I said, we were really puzzled for a long time about how we understand this transition between strong and weak and what it really means, and kind of having a toy model for it is something that we are quite happy about. And then, yeah, we think there is some relevance for quantum annealing. I also feel that we didn't find anything that makes things better for quantum annealing. Definitely not. I think maybe if we discovered anything, is that, well, even I would say rediscovered, is that the strong coupling limit is as good as the coherent limit, and that's pretty bad. so that's where we are. That's an optimistic tone for ending the conference. So, and then, yeah, and then in the near future, we want to look at basically finding possibly a model that makes all of this, puts all of this in the context of a sort of more realistic, strongly coupled environment, and I think we are on track to do that. And I want to just flash this. So I want to thank DARPA and IARPA again for their funding, and yeah, I'll put back my outlook here. And yeah, thank you. So.
Oh, do you want to grab your laser pointer and depart?
Yeah.
Thank you very much.
Yeah, sorry, this was long. I didn't follow really
No
the
problem.
guideline here.
Well, you were fighting with the technical challenges.
Yeah, that's, yeah. But
Apologies for that.
yeah.
Okay. So we have time for a couple of questions. Thanks, Paul. Safe journey.
Thank you, everybody.
I'm confused by the topology of this microphone. That's extraordinary. Okay, so we have time for a couple of questions.
I have a basic question.
Andrew.
Thanks. I actually have a couple of questions. One of them is basic. So when you showed the spectrum and you showed a crossing, what happens at a crossing? So are these kind of parity protected and they don't interact, or is there? So there's no transition between these two states?
Yeah.
Okay.
There's no transition. So the model is very basic. There is basically no, there's nothing that can take you, where was, oh yeah, sorry. Yeah. So this is essentially real crossing in this model. There's nothing that could take you between these two different branches here. So there's no dynamics here. You just keep going across that crossing. Yeah.
And the other question was, this is all fully consistent with the Lanting et al. Paper on the spin bath polarization, as far as you know?
Yeah, although this is very interesting, we don't look at the same physics. It would have been interesting to do it. We didn't have really a chance to do more experiments in that direction. It would be interesting to see how things compare. But I think one thing that is at least interesting is that I think we realized that because these qubits are different in some ways, basically you can probe a different regime in terms of this physics, So this relationship between the noise, the noise strength. So I think generally the physics depends on the relationship between the noise amplitude, the W, the temperature, and the delta, the gap delta. And I think we are kind of in that 3D plane. We are in a fairly different place to see some other things, which was very interesting too. Yeah, for us.
Thanks. Any other questions? Yeah, Philip.
So as you showed, some of your results, like the experimental results, are not exactly matched by the theory. And like here the question is it possible even to do some sort of quantum process tomography to identify, the map, the noisy map?
Yeah, this is a great point. Actually, there's kind of a funny story with this experiment. So there was, we wanted to do some of that, and we could have if, sorry, do I need to go? Well, yeah, probably that's the right slide. Yeah, so this processor has actually microwave control lines. So in principle, you could apply pulses and do process tomography and so on. And there would have been maybe other ways to do this by using Landau-Zener, kind of a coherent beam splitter, but there were some issues with operating this. So, for example, for Landau-Zener, there were problems with operating this part fast, and we couldn't do that. So this would have been interesting. But I don't think, in a way, it wouldn't take us much farther in the sense that there is no theory really for this intermediate regime, something that says kind of what's happening in between for any strength of the coupling, as far as we know. So I think in a way that's still something to be explored, because basically derivations of open system dynamics, they rely on these two different limits. There are more. There are some approaches, some of them more based on more on numerics. So for example, methods like QAPI to do numerical modeling of a spin oscillator bus. That's one of the things we are trying. But no, as far as we know, no analytical theory that's kind of available.
And similarly, like even if not going to full process tomography, then trying to maybe identify some, because at least that was my first impression when I saw your data, was that I see there's some signatures of non-Markovianity, and some of the models that like weak coupling model is like close to Markovian. The other one with ohmic buff is also Markovian. So like you cannot capture these effects with those models. So like is there any possibility of trying to find some sort of signatures of non-Markovianity and then adapt based on that something to your model, like super ohmic or something like that? In particular, even like the easiest way to see something would be probably to start with in the excited state and look at the same curves from like a flipped version.
Yeah, so it's a very interesting question. So there is a kind of a trivial form of non-Markovianity in this system, 1 over F noise. If you think of the classical 1 over F noise, this we understand very well, and it's non-Markovian in a trivial way, right? Just because basically the noise changes it has infinite correlation time, sort of. Yeah.
Yeah.
And yeah, so there is that part. But now to look at effects going beyond this, yeah, this is a great question. I think you need to do indeed, you need to use state analysis tools to do this properly. So this experiment does not directly probe this. Although I think the results are essentially consistent with this model that is basically a very non-Markovian type of environment, but it's not a direct probing
Okay,
of
thanks.
that.
Thanks for the talk.
Thank you.
Maybe one quick last one, if anybody has a quick last question. If not, let's thank Adrian again for a very interesting talk. Thank you, Adrian.
Thank you.